My name is Charles Parker. I'm the VP of Machine Learning Algorithms here at BigML. And today we're going to talk about fusion. The first thing we're going to talk about is exactly how you create a fusion, when you would create a fusion, and why, and how you do that with BigML. The second thing we'll talk about is some pros and cons. So there are downsides to using a fusion versus one of the standard single model types that we offer at BigML. So we'll talk a little bit about what you stand to gain and lose from creating a fusion. And then a couple of asides that we'll use to kind of motivate our creation of fusions. And those asides happen to coincide with various functionality that we've added to the platform in the last couple of months. The first thing is prediction explanations. So the ability to take a specific point in a data set, a specific set of inputs, and ask what is driving the model's predictions at that point. And then also our new text processing options. So we've expanded our text processing capabilities, and we're going to use those two things, prediction explanations and the new text options, to kind of motivate cases where you might want to use fusions as well. So we'll dive right in. And point one here, what's a fusion and how do you create one? So a fusion is kind of modeled after this idea of a mixture of experts. So in the traditional expert system setting, you have an expert, you have somebody who knows how to take inputs in and produce some output, produce a prediction. You know, there are examples of this in the ML world, of course, the models that you create, but also this is true in the real world, right? You go to a doctor, they're an expert, they take input in as your various features, your height and weight, as well as any medical tests they might order. And then they use that input to produce a diagnosis, a prediction about something. So that's a simple kind of formalism for how expert systems work. You have an expert, they take in your inputs and they produce your outputs. And ML works the same way. When you train a model, finally, it's going to take in some inputs and produce an output. The question here is, what do you do when you're unsure of whether that expert is any good at what it's doing? And of course, we have every reason to be suspicious, right? ML systems, as much as they, try to explain themselves, as we'll see in a bit, you should never take their predictions at face value, right? You don't know exactly what they've learned. And it's the same thing with experts in the real world. You go see a single doctor, they have their own set of biases, they have their own set of, weak points or gaps in their knowledge. And so you have every right to be suspicious when somebody makes a prediction and you don't know exactly how it was made. And so one of the ways to kind of work around this is just to get a bunch of experts together. So you go to several doctors to get several opinions, or in the ML case, you train several very different models. And then you have them all make predictions, and you have those predictions aggregated together by some function, and then the aggregate of those predictions becomes your final prediction. So in this way, you sort of mitigate this all your eggs in one basket problem, where you have a single expert, you have a single model, which knows how to do things in a single way, and you kind of spread that risk across multiple experts. This is, something we do in the ML world already with ensembles, and we'll talk a little bit about how ensembles relate to the fusions that you create. But also they do this in the real world all the time, right? If you pay attention to economics at all, and they're making projections about GDP growth or about unemployment numbers, they never just go to an expert and get a prediction. They go to a bunch of experts and they'll aggregate the experts' predictions by taking the mean or the median of those predictions. And that's the final thing that you see in the news, is an aggregate of what all those experts think. So this being BigML, there's a whole bunch of ways to create a fusion. Of course, you can do it in our domain-specific language, WizML. You can also do it from our API directly, just by posting to our API. You can see the code there. The post is basically a list of models, and that's all a fusion is. It's a list of models that are going to make their predictions separately, and then we're going to aggregate those predictions together. You can do that from any of our bindings, of course, which wrap that API call in kind of nice code. And then there's a couple of different ways to do it from the interface. So on the lower left there, you see you have a little button that says Create Fusion right in your list of models there. And then also, if you train Optimal, you can select any of those models that you learned in the Optimal and create a fusion out of those. And this can be nice, because of course Optimal has searched the entire space of models looking for the best ones. And so if you create a fusion of those things, sometimes they'll, correct each other's mistakes. So let's see that in action in the dashboard here. So you can see, here's my list of sources. I'm just gonna go to my list of models here, my individual decision trees. You can see I've got the list of models there. I've got the fusion up here, the fusion button up here in the upper right-hand corner. And so if I click on that, I can select one of my models here, or two of them, and then I just go to create fusion. And when I do that, I'm thrown into this new fusion screen. And here, if I want, I can add models of any other type, any other supervised type. I can add ensembles, or I can add logistic regressions, deep nets, and even I can add fusions to this fusion, right? I can add fused models that I've created before. I'm not going to do this right now. I'll do it a little bit later. I'll create a fusion, and you can see what the output looks like. But essentially, the output is just going to be this list of models that will all make their predictions separately, and I'm going to aggregate them together. You'll see, add one more here. If I add one more model here to my fusion, you can also see that I could weight these things. And so what does that weight mean? Basically, that's going to be a factor by which the prediction is multiplied before we aggregate all the predictions together. So for example, if you have the suspicion that model 1 here is a lot more reliable than model 2, you could give model 1 a higher weight. You could say, I want to weight model 1 5 times as high as model 2. And there's a number of reasons you might want to do that. The first is that if you again think one model is more reliable than another, then that's one reason to do it. There might be a history factor. So if you've already created a model, you've already had it in production for a while, and you think, I know this model is very good, it's already proven itself in a real world setting, you might want to weight that model higher than a new one that you've just trained that you think has promise, but you're not totally sure. That's one reason you'd want to set the weights. And then a final reason that comes to mind immediately is if you've got some sort of time-based retraining going on. So if you have some data comes in, say the data from the current month, you train a model on that data, that month's data, you run that model in production. Meanwhile, you're gathering data from the next month. And then when the next month finishes, you train another model and you add that back to the fusion at a higher weight. So essentially, you always want the latest, most recent model in the fusion to have the highest weight, because of course the recent past is more relevant to predicting the immediate future than the distant past. And so you'll have this kind of distribution of weights where the models way in the past have very low weight, and the models from very recently have higher weight. And so that's a strategy some people use to make sure their models' predictions remain updated as training data comes in. So how does this relate to the other techniques that BigML offers for putting models together? The most obvious one that we offer at a first-class interface level is the Ensemble, so the random decision forest or the bag of decision trees. And this is essentially a very similar thing, right? You've got all these trees, they're all learned on subsamples of the data, so they're all a bit different. And then they make their predictions independently, and you aggregate those predictions and you get some final prediction. And you aggregate them typically in much the same fashion. It's just sort of an additive aggregation. The main kind of functional difference between ensembles and fusions is that ensembles, although the trees are a bit different, are fairly uniform, right? They're all learned on the same features. They're all learned via the same technique because they are decision trees. And so they're all going to have some of the same strengths and weaknesses. We try to mitigate this in random forests by kind of randomizing which features from the data set that they're built from. But they're all very much the same, right? They're all these trees. In fusions, you can have a diversity of input models. So you can use, again, as you saw earlier, you can use any model type that you want to make a fusion. And also it's possible to use entirely different feature sets to make the fusion. So if you have kind of a carefully tuned model based on a text field, for example, so you've tuned, the various text parsing parameters for that model, you've selected a type of model that deals very well with those word occurrences. You can fuse that with a model that makes the same prediction on a bunch of numeric features, say with a logistic regression. And so you can get kind of a diversity of approaches that's not possible with the kind of the standard off-the-shelf sort of random forest or bagging approaches. A couple of other things that fusions are not, first of all, one is stacking. Fusions are not model stacks. In model stacking, you have this mixture of experts, and you replace that aggregation function with another expert whose only job, this meta expert's only job, is to trade off the various predictions of the base expert. That's a little bit different and kind of more difficult logistically to do, because you typically split the data set into two parts. You use one part to train the base level of experts, and you use the other part to train that meta expert to aggregate their predictions together. And so this is not stacking. We only have the one layer of experts here. And then finally, this is also not boosting. So boosting, you remember, instead of just a straight kind of parallel mixture of experts, you have a bunch of experts that are trained to learn from one another's mistakes. So the first expert learns some sort of baseline model. The second expert learns when that baseline model is wrong. The third expert learns when the first two experts are wrong, and so on and so forth. And then by aggregating the entire chain of predictors together, you get your final prediction. All right, so hopefully that gives you an understanding of what fusions are and how you create one. Let's get into some of the reasons you might or might not want to create a fusion. So first of all, comparing and contrasting single models and fusions. One thing about single models is they tend to have these areas of ignorance, right? So for individual trees, for example, if there's a place in the data space that only has 1 or 2 points, we'll overfit to those 1 or 2 points, right? We'll split until those outlier points are isolated, and then we'll try to make a prediction based on those outlier points. And so you'll get this kind of instability where outliers are fit very closely, and the prediction doesn't really match reality because you don't have enough data to make it out there in those outlier areas. Similarly, logistic regressions have the opposite problem, right? They're these very high bias models, which will fit the bulk of the data, and then kind of outliers be damned, right? If you have these outlier points, even if they're informative, or even if there are quite a few points in some area, if they don't match what the great bulk of the data does, that you're not going to get good predictions on those kind of fiddly little areas where you might have enough data to make a reasonable prediction. Fusions, on the other hand, are a bit more stable. And you gain the stability by, of course, combining these different model types. So instead of having one model type with its own specific weakness, you combine several of them, and so sometimes they can mitigate one another's weaknesses. The predictions might not be better overall, but the errors will sort of be smoothed out over the entire data space rather than isolated in these particular areas. Second, and I just talked a little bit about this, regions of the input space and single models might have these underperforming predictions, and with the fusions, it tends to smooth these errors out. So again, with that stability, with the notion that the prediction quality won't vary so dramatically from one point to the next, you'll also get the case where the errors won't be concentrated in one area of the data space. Single models in general, our single model types are pretty fast. So decision trees, logistic regressions, we're talking about dozens or hundreds of multiplication options or dozens or hundreds of feature tests. This happens in microseconds on a modern computer with any power whatsoever. With fusions, you get a few ensembles together with a few thousand trees each, maybe a few deep net models together that have a few thousand nodes each. That starts to be millions of multiplications, millions of feature tests, right? And so at that point, you'll have models that are several orders of magnitude slower than what you would get if you just stuck with a single model. And that doesn't sound like a big deal, like, oh, it's the difference between microseconds and milliseconds. Why would that be a problem? And it wouldn't if you're making one prediction at a time. Typically, that's not a big deal. However, if you get 10,000 or 100,000 data points in, and you need to make predictions on all of them, that's the difference between something taking minutes and something taking maybe days, right? And so, speed is not a problem with these ML models until it is. And that point tends to come quicker than you think. And then finally, the convenience of evaluation, if you want. With Optimal, we've got all that done for you, right? We do cross-validation in the background. We kind of have the sensible search through the space of possible models. It's easy to do that when you're only learning a single model. When you're trying to learn any possible combination of models, you're going to have to basically do that validation yourself. So you're going to have to hold out some data. You're going to have to try these combinations by clicking around and then by evaluating them on the held out data. One thing you probably noticed in the last slide is I didn't really talk about performance, right? I didn't say anything like fusions are going to be, quite a bit better performing, and single models you're going to find their performance inadequate. That's typically not the case, right? Typically, ML models, single models do their job fairly well. And when you have a fusion, when you have a bunch of ML models together, they're typically just doing that job that they do very well over and over again. So combining them, especially on easier problems with low error rates already, often doesn't result in a huge performance gain. Of course, the exception to this is if you learn several models with significant feature diversity. And we'll show you a bit about how to do that in the second aside in a few slides. If you need huge performance gains, if that's what you're after, you're typically better off doing manual feature engineering, or even better yet, acquiring more and more data, cleaner data, data with better features. Those are the ways you're going to get improvements in the models that you make, or rather, it's more likely that you're going to get improvements from those things rather than just kind of fiddling around with different combinations of models. The reasons to do it are, first of all, for that stability. So if you see areas in the data space where your model is performing inadequately, fusing together models that even have the same error rates can tend to smooth out those errors and make the model's predictions look a bit more sane. And then the other reason to do it is to improve the performance or the importance profile of the model that you learn. And this is another little spoiler alert for the next set of slides, which we're going to talk about. And this is functionality that we've added to the platform recently about prediction explanations. So prediction explanations are ways of explaining the prediction that you're getting out of a model in a single data point, for a single data point. So rather than just kind of explaining what features are important to the model in general, we explain what features are important to the model for this particular data point. And so in the former case, you'll see if you create an optimal, for example, you'll see that all of the models that we create for you, or all the models except logistic regression models that we create for you, we give you this field importance plot. So we show you the 5 most important fields for the model as a whole. So here's an optimal that I've created earlier. If we look at the important fields for this DeepNet model, we see that the most important field by far is your blood sugar level to predict whether or not you have diabetes, and then there's other lesser factors here. If we go down to a single tree here, which still performs fairly well, we see that the blood sugar level is not quite as important, right? And there's some other things down here like the triceps skin thickness, which is a measure of how much body fat you have. That appears in the top 5 most important fields in this model, where it doesn't in the DeepNet. So this can be a reason to do a fusion, right? If you look at this importance profile and you say, oh, that, the top model is ignoring something that I find very important. The bottom model, even though it performs a little less well, is picking up on something that I find very important. And so if you wish that top model would take that thing into account, that the bottom model is taking into account, oftentimes you can fuse their predictions together. You get a model that kind of respects the value of that field that the lesser model is paying attention to. The fused model will also, by definition, be paying attention to that, and you'll still get roughly the same quality of predictions as you would. And so if you need to kind of smooth out your importance profile, you need to get an importance profile that makes more sense to the human operator. That's one reason to create a fusion. With these 2 models that you're seeing here, their overall importance profile is sort of similar, right? They're not so very different from one another, but there are regions in the input space where their predictions are very different from one another. And so this is where prediction explanation comes in. It allows you to go to a particular region of the input space to give yourself a particular set of values and see what's most important to the model at that particular place. And so, for example, if I go here, I can go to predict with this individual model. And it'll take me to a form here where it's got sort of a median patient, right? So let's say I'm interested in this place in the input space. I'm interested in what is important when I make a prediction for this patient. I can go down here to my little compute the explanation and predict. And you can see at this point in the input space, diabetes pedigree is the most important thing. That's very different from what it says back here, right? For this same model, plasma glucose is the most important thing overall. But for this particular patient, diabetes pedigree is crucial. So if this is an important patient, for example, or if this is somebody we want to make sure that the diagnosis takes into account certain important things, this might be a reason to do a fusion as well. You think, oh, diabetes pedigree, maybe that's not the thing that I want to be the most important thing for this region in the input space. If you want to smooth this out a little bit, if you want the model to take into account maybe some different things, you can go back here and look for a model that takes into account different things for that region in the input space. So for example, if I go to predict here for the individual tree, and you can see I have the same set of input fields here, because again, this is just like the median patient. And I do the prediction explanation. Wow, now plasma glucose is very important for this particular patient, right? And that's quite different from what I saw, from what we see with the DeepNet model. Now the DeepNet model is a bit better predicting overall, but it has this feature where the diabetes pedigree is the most important thing for this individual patient. If that's not true in your mind, if you want to change that importance profile a little bit, a way to do it is to fuse these two models together. Again, because this model here is putting a lot more weight on plasma glucose and age. And so if I skip back to my optimal here, you can easily create a fusion of those two models just by ticking the appropriate boxes here and going to create fusion. This will throw you back into the new fusion creation dialog here, where I could add more models if I wanted to. I don't. Let's say I just want to add these. And so you can see it throws up a partial dependency plot, just like it does, this interface does for a lot of our other model types. And the important thing about this is that the individual tree, you can see the splits of the individual tree, right? These axis aligned partitions between these areas of color here. You can see the splits that the individual tree made. Normally, for the individual tree, this entire area is going to make the same prediction, right? You'll have no nuance within that area. But because we've combined those predictions with a DeepNet, you see that the prediction varies even within that area, right? And it varies kind of dramatically. It goes all the way from, you know, about 80% for someone with very low blood sugar, all the way up, or all the way approaching, you know, 50-50 to someone who has higher blood sugar. So there's some level of variance within the splits that the original decision tree made. And so this is kind of a visual confirmation that you've got a different model here, that you've got a model that finds different things important. And in fact, if you go up here to the fusion summary report and you look at the importance profile, you can see that plasma glucose, you know, very important because both models found that important. But now the diabetes pedigree is important and the pregnancies are important, but things are a bit different than they were for the original model, right? And for the original DeepNet model, diabetes pedigree was up a slot, and so this is a very different set of priorities than it was for the originating models, for the two models that I built this fusion from. And so now let's talk about one more reason you might want to create a fusion. So in the previous set of slides, we saw how you could use a fusion to kind of change the importance profile of the resulting predictions. If you found that certain fields were important for one prediction, not important for another prediction, you wanted to change the importance of those fields. You wanted the model to be basing its predictions on a greater diversity of things, maybe. That's one reason to create a fusion. Another reason to create a fusion, as I said in one of the initial slides, is if you've got two models that are operating on kind of a diversity of features, right? You have two models that are operating on different feature sets. And one way to generate different feature sets from the same initial data set is to use the new text option. An aside about the new text options, we have 15 new languages. The new languages that we have for those new languages, we of course know the stop words for those languages. We know all the words that are in those languages. We know how to stem words in those languages, so we know how one form of word maps to another in the various languages. And then also we have new stop word options and term filters. So you're able to select the aggressiveness of your stop word removal. So you can remove common words in the language very aggressively, meaning we're gonna remove almost all the common words in the language, or you can dial down the aggressiveness so that you only remove words that are extremely common in the detected language. And then we have a bunch of term filters. You can remove words that aren't in the dictionary for the language. So if you wanted to remove, you know, say foreign words or gibberish, you could use the term filters for that. We can remove HTML tags or numbers. And then we have this n-gram selector here that allows you, instead of just taking single words in the language as terms, you can take phrases that are 2, 3, 4, or 5 words long, and you can have those be the terms in your resulting models. And if you do that, you can also turn off using single words. So if you want the models to be based on solely words or solely phrases of 2 words or greater, you can use this little n=1 selector to remove all of those terms that are only, or all of those terms that are only 1 word long. And so what's nice about this is you can create from the same source, you can create data sets that are very, very different, right? That have very, very different features by doing things like changing the level of stop word removal, removing all of the common words in one model and removing none of them in another model, or using multigrams and single term filtering. So you have one model that's learned basically on only single word phrases, and another model that's learned on only phrases that have a number of words greater than 1. And we're going to see that in a second. You can turn off stemming. So you can say, I don't want to group word forms together. I want all of those word forms, player, playing, played, to appear as separate terms or separate features in the resulting models. And then, of course, if you have models that have a diversity of features, you create a fusion from them, and they may very well be able to correct one another's mistakes. Let's just see an example of that. So this is a data set that I've created from a source that has a bunch of movie reviews in it. You see the full text of the reviews in the source is down here in this reviews feature. And you can see the single words that occur are sort of the words you'd expect when reading a movie review: atrocity, bastard, that's unfortunate, flirting, impulse, just a bunch of words that you wouldn't be surprised to see in a movie review, right? But yeah, terms that appear in movie reviews with no, you're unsurprised to see those terms in movie reviews. And then we've got another score up here, review score average, that allows you, that is the aggregate score of all of the reviewers, reviews, essentially. And so one thing you can try to do is you can try to use the text of the review to predict what sort of score that is going to be assigned to this movie, what average score. And so if you do that, you get a decision tree like this. And basically what this tree is going to try to do is it's going to look for words that mean this is a terrible movie. So, unwatchable, ugh, abysmal, spewing, oh God. Okay, so obviously there's a lot of things that indicate that this might not be such a great movie as you move down the chain of words here. And so that's fine, right? That's what these models are made to do, especially these decision tree models. They're made to peel off bits of the input space where the prediction is very different from the input space at large, right? So it sees this word, it sees several reviews containing this word, it says, okay, this is probably a bad movie, and then it does that over and over again. That's fine. That's good. It's doing what it's supposed to. Now, if we create the same data set, but we create it with multigrams only, so that's where I used our new text processing options to say, hey, I want 2, 3, 4, and 5 grams in the model. So I want 2, 3, 4, and 5 word phrases as features, and I want to ignore all the one-word phrases. And the reason you do this is because unless you ignore all the one-word phrases, they tend to dominate, right? Single words are a lot more common, kind of by definition, than pairs of words or triplets of words. And so the model will tend to ignore pairs of words or triplets of words just because they're far less common than the single words. This isn't to say that those pairs of words or triplets of words are not useful features. And so that's kind of what we're exploiting here, is there's these features that the single word model doesn't use, it doesn't need to make its prediction, because it does perfectly well with the single words. But they're going to be uncorrelated and still useful. So if I mouse over my reviews here, you see I've got pairs of words usually. Occasionally there's a triplet of words, but mostly these are pairs of words that you wouldn't be surprised again to see in a movie review. And so low budget, funny movie, enjoy watching, all phrases like this that again are common in movie reviews. And so if you do the same thing, you'll see that the same thing happens, right? It's looking for phrases that indicate that a movie isn't very good. my favorite here is Complete Waste, I think. Probably that's not going to be a great movie. But they're all two-word phrases, and they don't coincide at all with the one-word phrases that we were seeing in the other model. This is one of my favorites here. You can see it's looking for the phrase falls flat, which of course is going to indicate that the movie's not very good. But those two words by themselves, falls and flat, don't really have a negative connotation. Maybe flat a little bit, but certainly not as negative as most of the other words that we were seeing in the other model. So this is a case where you've got these two features that taken apart don't mean anything, but when combined into a single feature, they're extremely informative, right? And you can see just how informative 90 out of these 1,000 movies, so 10% of these movies-ish, 5 to 10% of these movies contain this phrase falls flat. That does a great job indicating that it's not a very good review. And so that's an important feature that would otherwise be ignored unless we had these new, if we didn't have these new text processing options. And so to tie this back to fusions, the reason to kind of make a fusion out of these two models. So if I go back here, I think I actually did this initially. Yeah. So the reason to make a fusion out of these two models is because the feature spaces are completely divorced from one another, or not completely divorced from one another, but not terribly well correlated. And the reason for this is because when people say that a movie is bad, when people write a bad review for a movie, they don't typically use every possible word you could use to say that a movie is bad. They only just use a few. Even the features that are all very well correlated with a movie getting a low score, those things don't tend to be correlated with each other simply because people don't tend to use all of those bad features at the same time. They choose a very small percentage of the possible ways you could say a movie is bad, and they use that. Otherwise, the review would be, extremely long and redundant, right? It would say the same thing over and over again. That's generally frowned upon when you're writing. And so you've got these two models. They both detect whether or not a movie is terrible, and they do it with features that are mostly separate from one another. So this is an opportunity for those models to correct one another's mistakes. And so you're likely, I'm not going to go through the full business of creating the fusion and holding out data and doing an evaluation, but there's a significant chance that when you have a situation like this where you're able to create two models on two different feature sets, where those feature sets are not very well correlated, that's a case where you can use fusions to possibly improve your model's performance, right? The combination of those two models, the prediction is going to be more powerful than either of the single models alone. And this is the case when you see Kaggle competitions, where often the best model in the competition will be a fusion of several different models. This is the reason why, essentially, because you've got two kind of separate teams or separate guys, separate women working on their model in different ways. So they're using a variety of different pre-processing techniques. Maybe somebody uses PCA to do feature pre-processing. Maybe somebody uses k-means to create a new feature space. So you end up with input spaces for the final supervised classifiers that are extremely different from the original input space, right? These people have done so much pre-processing that their models end up learning against features that are incredibly different from one another. And so by fusing those two things together, if both models perform very well, the combination is likely to perform even better because they'll have different weaknesses. They'll be able to correct one another's mistakes. All right, that will be the close of the presentation there. If you want to learn more about fusions, you can see all of our usual bevy of blog posts that we post showing how to do this from the API, how to do this from the dashboard, some cases where it works well, and maybe a little more information that you didn't know about fusions. We also have the dashboard documentation and the API documentation, as we always do. And then we have the blog posts about separate blog posts about our new text processing options, if you're interested in those. There's also blog posts that are a little bit older if you want to learn more about prediction explanation and how we do that. You can dig back a little bit in our What's New archive for a couple months, and you can find that blog post as well.